All right. Hello, everybody. How you guys doing? You okay with a storm coming? Some of you know. How many of you are completely new to this? Anybody? Okay, so some of you are not ready because you've experienced it too much. Well, please be safe. We're going to get a lot of that probably. Um, I'll talk about what we're going to do Thursday here in a moment. But first, I've got a couple guests coming to tell us about the Water Brigade. It's an organization on campus that does wastewater type of projects in developing countries. Something near and dear to my heart. So uh, please welcome Olivia and Daryl. Give a few minutes talking about stuff, talking about their group, and I'll let you have it from here.
Thank you.
I can advance where you can or whatever.
So we're Global Water Brigades, LSU. We're a chapter of a nonprofit national organization called Global Water Brigades. They also have stuff like medical brigades and grant brigades they do, but we're specifically part of their water chapter.
So just bouncing off of that, just more of what our purpose is on campus. Not only do we help build water filtration and pumping and delivery systems in developing countries, but we also serve locally, because if we don't make an impact, in our local communities, then what are we really, going other places to go do if we can't take care of home? So this is just a little bit about purpose and who we are.
So kind of what we do. What we're really well known for as a club is that, of course, we do a brigade to Central America every year during spring break. Last 2 years we went to Panama. I've gone twice. This year we're going to Honduras. And then we also, of course, as a club, we think it's also important to do local service, which is kind of something more unique to our chapter. We've done work with like Habitat for Humanity. We've done hurricane relief stuff. Sometimes we'll do work with Stormwater Coalition, where we'll clean up trash around bodies of water. Like I think we did one near the Capitol last year, and also we've done cleanups around LSU lakes.
So this is our why, and kind of bouncing back to local service, and we got perfect timing, but also really bad timing with the hurricane coming tomorrow. Off script here, but in the case of a hurricane, we always volunteer, and God forbid anything happen or major damage. But we will be there on the next break volunteering. Remember, I joined personally because I saw an opportunity that we were putting out my freshman year after Hurricane Ida, and we spent a week over winter break, in Houma, Louisiana, volunteering there, helping to clean up with the efforts as well. And so those are just a few reasons why we do what we do and why we serve locally as well as abroad.
So, some of the benefits of becoming a member, of course, if you don't go on the brigade, you try in the club. Great in the community, a lot of amazing people that have great hearts and doing some amazing volunteering work. But as brigade, it's also awesome life-changing experience. You spend a week in a different country with a bunch of great people that you get to know really well. But yeah, we get there's travel opportunities. In general, we try and be like a high impact, low commitment club, which extremely one.
Yeah, we usually have one service event or two service events a month, only one meeting a month. We're not one of these clubs that makes you stick to having all these membership points and service points and all that. We just want people that are motivated to make a difference and come home.
So kind of talking more about the brigade, this is kind of where this is probably most relevant to you guys. I took this class last semester in the spring, and I thought it was really cool because when I went to Panama, when we were kind of working on these rural water systems, they're because they're out really rural areas, they're typically pretty simple and how they're designed. It's not like you're going into a massive Baton Rouge plant where you have no idea what's going on. You really get a chance to see all of the different processes that you learn about in the class. So for instance, here I think a couple minutes after this photo was taken, we were actually looking in to check the turbidity of the water in this tank. This is a tank where they do coagulation, flocculation, and sedimentation all in one process, which is kind of interesting. But they basically showed us how the water was they were agitating the water to get the particles to collect, and they would let it filter out. And then kind of behind this, not shown here, there's a chlorine tank where they would send the water from these tanks to get, some chlorine put into it so it can drum. And then we were also kind of working on the piping system, so we were like gluing, cutting PVC pipes. We laid a lot more pipes than you see here. We did a lot of work in expanding the distribution system. We actually, if you've taken EVEG 3200, sorry, we also used EPA net, which is one of the programs we used in that class. So there was a lot. Not every brigade is like this. There's a lot of variance between them, but it was really cool that we got to kind of use all these things that I was using in like my engineering classes at home. So it was a really great experience. Also got to practice a little bit of like my Spanish knowledge over there, which is really cool. Of course, but yeah.
If I can pick up as well, I'm a biology major, so I don't know anything about EPA yet, and I know the very basics of flocculation, and we did some pH testing of water too. That's about the extent of my understanding. But it's not all work. Well, let me get back to the other thing we did up in that top left, right corner. Is we interviewed the people living in the community, especially the women, to get their sense on like what are the public health effects of the lack of access to clean water, and what can we be doing to make sure this is a sustainable project, and we're not just here, for a week to do our part. We worked in like a week there in Panama community, but our engineer we were working under, this is Mr. Vaughn. He had been there for I think 6 months already, working alongside the people and planning and doing everything that needs to lay the groundwork for us to come in and for other future groups to come in after us and continue the project. And then there's a little fun there as well. Last day we had finished most of our work we wanted to do for the week, so they wanted to play us some basketball, which was fun.
We also did some engineering surveying, which like GPSs as well. Well, I missed the last kind of thing we did. But yeah, there's any major can find something that's really relevant and like really powerful.
And here's some more of just the local service things we do. This is a part of the lake cleanup. I think this is the county lakes. There's us at Habitat for Humanity, and then there's us in the lake cleanup. When the lakes were low all last year, I think that was last fall. And then I think that's the CAA, like the
I'm not sure. Ecology? I'm not sure.
Yeah.
That was an older picture.
Yeah.
We do all kinds of stuff. So meetings kind of got messed up. The schedule wasn't super accurate. We were supposed to have our first meeting last week, but there was flash flooding, so we canceled it. It's supposed to be this Thursday. Don't know about that. But at the very least, if you're interested, we're definitely having a brigade info session on Thursday, 26th. There'll also be a general club meeting. But yeah. And then our pilot and route meeting directors are next week.
Thank you for your time.
Thank you.
You guys got any questions?
Questions, comments, concerns? Thank you, Dr. Snow. Really
All right, thank you guys. This is fantastic to hear, and I'm so glad to hear that it's doing well.
Thank you.
Thank you.
All right, I'll leave that up for just a moment if you guys want to check on that. I've heard great things, and I know that the faculty advisor, Clint Wilson, is also a great guy, and yeah. So love anytime I get a chance to interact with him. He just moved from our department, the Civil and Environmental, over to be Dean of the College of Coast and Environment. So he's their faculty club mentor. There used to be an Engineers Without Borders group. Technically, I'm the mentor for that, but it doesn't exist, and I send everybody to Water Brigade. So if you're at all interested in this type of thing, that's the way to go. And I think it's actually best that way. So thank you all. Thank you very much. All right. All right. So, class today, we're going to pick up in a moment with kind of where we left off. We'll wrap up the last bit of chemistry and then launch into sedimentation and kind of generic intro to drinking water treatment. Before that, I wanted to talk a little bit about what are we doing Thursday, and all of that. I got an email this morning before my other class saying, okay, we're planned for online classes on Thursday. So I guess LSU thinks that we're all going to be fine and with power and everything, which might be the case, and I'll happily give a lecture from my office at home. I started this whole format back in COVID and the live streaming and everything, so it's pretty easy for me to just work from home and lecture that way from a chair, or be here and do that. So Thursday will not be here for sure. I know that much. Whether or not we're going to be live kind of depends on if I have internet and power. So what I will say is I will plan to be there or here on live, rather, not here in this building. You have all the information about the YouTube channel. I could show you right now. Maybe I'll pull it up while I talk. You will be able to engage with me by asking questions, and it'll pop up, and you'll see. You'll be able to see what you say. Let's see if I can find my own channel. Well, you know what? We'll do this. So if you go to youtube.com/@snowslab, that should bring you, well, I guess that works, to where we're live right now. So now we've got YouTube Inception, but my point is that you can come over here and use the chat. And ask me all the questions you might want. And I will then see it on my end, and gonna break the brains even a little more and kind of show you, sorry, that didn't work very well. Yeah, there you go. And I'll be able to see it pop up for me right here, because this is kind of what I look at while I'm talking. Now, let's try to, oops, that's not what I wanted to do. And now I'm having a slight bit of trouble here. Just need to grab that, there we go. Okay. All that to say, you'll see it, and you'll have this view, you can make it full screen, all that. So, it'll be there. If I'm live. So question is, am I going to be live? Well, that'll depend a lot on our particular conditions. Do I have power? If you're going to be there live, it depends on if you have power and internet, right? So all this to say, there's a pretty good chance that, and hopefully I have power, I'd like to have AC and all that, there's a pretty good chance I'll be live and you can see it then. If I'm not there live within 10 to 15 minutes of our normal class time, just assume, and you didn't hear from me, just assume no class, okay? And we'll make it up or whatever later. Typically, it's not uncommon to have 1, maybe 2 missed lectures in the year, and usually LSU is like, okay, 1 is fine, but if we're missing multiple, then have a makeup session. Okay, so we could do that if we need. I'll plan to go ahead and give it a shot, but I understand if that doesn't happen, and I think you do too. And I understand if you don't make it there, but it'll be online for you. Okay? So just like normal. Of course, a few people emailed me right before class, but I was busy with the other class and everything. So for those of you, if you're watching now, that's the right thing to do. If you had to evacuate or whatever, catch up later. No problem. Just gonna roll with it. All right, any questions or concerns? All right. Okay. So with that, definitely will not see you on Thursday, but you might see me through the internet. Okay. If you did have some pressing question that you didn't feel like you could ask directly through the chat, you're welcome to ask me to hop on Zoom or something, and maybe I could save a few minutes at the end of the class and do that. But usually, I think it should be straightforward enough, and we can cover other questions when we return. All right, so last time we left off talking about reversible reactions. Specifically, we need this so that we can handle stuff that dissolves and chlorine and things like it that might change forms while we're using them for disinfection and stuff. So how does pH affect chlorine? That's kind of a question that we have to address and we have to design for. So we're doing a bit of chemistry so we can handle that. We talked about this equilibrium constant, and we described it as a product rather, not a sum, so it's not a plus, it's a multiplication of the products, the chemical products that happen from the reaction with their stoichiometric superscripts here as their powers. A lot of times it'll just be 1 and be very simple, divided by the reactants. So for the case of water, we have OH minus times H plus divided by the concentration of water. We're going to take the concentration of a liquid, pure liquid or a pure solid as 1. There are some slightly complicated reasons that holds true, but it holds true. Just don't worry about it. If it's a solid or a liquid, we're going to treat it as 1. So that gives us a way to understand how much of one or the other we have given some condition. So for example, if this is our water reaction here, if we add more acid, it's going to necessarily take away from the OH minus because it's going to push the reaction the other direction. So the pH scale comes out of that. So at a low pH, it's very acidic, and we end up with a lot of protons and not many OH minus. The reverse happens if we go very high pH. It's very basic. We have a lot of OH minus, very little H plus. Okay, so that'll hold true and similar for other cases as well. We also watched a little video talking about reaching equilibrium. For this class, we're pretty much going, if we're talking about an equilibrium reaction, we're talking about the time when we have already reached equilibrium. It doesn't mean there's the same amount of stuff. That's not what I mean when I say equilibrium. I'm saying the same amount of stuff going both ways, right? The little jars, right? So we might have a huge amount of H plus and a small amount of OH minus, but the amount of transfer has become equal, all things else considered. So that's what we're talking about when we're talking about equilibrium. You can almost think of it as some sort of like a seesaw balancing thing where sometimes you reach equilibrium, but you could shift you could have a seesaw that looks like this, the weight over here and a weight over here, and it's going to take a lot more amount of stuff on the left in this case to reach your equilibrium, right? Whereas a typical seesaw has an equal amount of stuff on either side. That's not very helpful. So your equilibrium might be when you have equal amount, or it might be when you have a larger amount, but you've found that balance between them. So there's several analogies you can look at. Don't worry too much about it. We're just saying the same amount of the same rate of reaction going both ways. And it does not mean it must be the same amount. Neutral pH is when we do have both an equilibrium and the same amount of acid and base. Okay, so we have some other types of reactions that we'll find that are pretty common and pretty important. The carbonate system, for example, how does CO2 dissolve? Why does it blow up out of a Coke can when you drop a Mentos in it, right? This is a CO2 gas exchange sort of system, and when you put CO2 into water, it will dissolve. So we'll go from gas, it will be in equilibrium with carbonic acid, H2CO3. And you can see we just basically added 2 H's and an O, kind of just joined them. That's this guy. So this is kind of like dissolving CO2 gas. So this will be in equilibrium, and then these two are in equilibrium, and then these two are in equilibrium. So that all told, this system has 3 different species, if we're just 3 different dissolved species, plus potentially gas. and they're pH dependent. So when they cross and they meet here, we have equal amounts between those two. We can be at equilibrium at any point here. We just shift the pH and find our equilibrium. We let the system settle, and we can find an equilibrium even if there's not equal amounts, right? So we could find equal amounts where these two cross, or we could be at a spot where we reached equilibrium here. We have a very small amount of H2CO3, that's carbonic acid, a lot of bicarbonate, HC3O-, and a little bit of CO3-2-, carbonate. So in these systems, we can have different amounts of stuff at equilibrium, and it's just sitting there, okay? Then we change the pH maybe, it adjusts, but it happens pretty quickly typically, and we reach a new equilibrium, and then we have a different ratio. So typically we're going to say we've reached equilibrium if we're talking about an equilibrium. We're not really interested in that moment where they are currently decreasing or increasing. So we'll see plots like this. I mean, in equilibrium chemistry, these plots are fairly common. And what this is showing is what fraction, what percentage of a given species is, or of the total carbon is, for example, in this form versus this form versus the other one, right? Okay, so one other consideration for equilibrium is pH itself. I already mentioned this with water, and there's one definition I'd really like to drive home here is what is the P in pH? It's just a mathematical operator. That's all we are actually saying. So pH means we're taking a mathematical operator on H. So H is proton, H plus, so it's P of H plus. And since this is a chemical system, we're going to describe this in the concentration of H plus. So we're going to say the molar concentration, so put the brackets on it, and say this is actually saying that some operator on the amount of acid we have. The operator, the P, is take this thing, take the minus log of that thing, and return the answer. So minus log of H plus gives us some value. That's pH. So minus log of H plus. So when we stop a moment and think about it, water has an equilibrium reaction. Water goes to H plus and OH minus. I already wrote this up, and what we might say is new here is the product is equal to 10 to the minus 14. Take a quick side note and say the units of these are always a little, there's some complicated reasons that they're tricky, but we kind of can ignore it. So don't worry too much about it. It will work out so that whatever it needs to be, that's what it is. We're gonna, so in this case, it's actually moles per liter squared, kind of. The denominator would be mole fraction, and each of these would be moles per liter. We're gonna just not worry too much about units in this one case. Just trust me on that, it'll be fine. So K then for water is 10 to the minus 14th. We could actually describe this as pK water, and if we take the minus log of that value, 10 to the minus 14, we get 14, right? If you remember, the pH scales goes from 0 to 14. This is kind of why, right here. So we can also write this value here, Kw, because this guy goes to 1. This is like saying this is equal to the H plus times the OH minus, the molar concentration. So if we stop and look at that, and we remember pH 7 is neutral, well, why is that neutral? Well, it's neutral because that's when we have the equal amount of base and acid coming from water. That's the OH minus and the H plus. So when OH minus and H plus are equal under this condition, And we are saying that's pH 7. Well, let's check to see if that works. So in this scenario, we could say H plus times, and I'm going to substitute another H plus because they're equal, should be equal to 10 to the minus 14. Right, that's simply taking this equation here and then substituting for, instead of OH minus, we're putting this in here, where it would have been OH. We substitute, and so we have H plus concentration squared equals 10 to the minus 14. So if we take the square root of 10 to the minus 14, we will find that H plus indeed is equal to 10 to the minus 7. So we take the P of this H concentration, which is taking the negative log of 10 to the minus 7, and we should get, and I think I misspoke earlier, that should be negative, right? Or no, that's fine. Negative log of 10 to the minus 7 is pH of 7. Okay, so this is how the pH scale works, and this is why it works. So P is that operator. We're saying P is negative log of something. So we could say P of X is negative log of X. Okay, does that make sense? Okay, so if you know the concentration of H plus in a system, then you know the pH. You just have to do the operator. If you know the value of OH minus, you know the pH. You just have to check and do the equilibrium, and you might have to do a little bit of solving, but you will know it. You'll know the value, and in fact, whatever it takes. Let's say you know OH minus, you don't know H plus, but you have to find it. You'll be given. I'll remind you that the Kw is 10 to the minus 14. So you'll know everything except for one value, right? If you're given the OH minus, you can solve the pH because, well, you have one unknown. You can solve that, right? That's algebra. And then, so you solve for H plus if you know OH minus, and you go from there. You have to remember the operator, right? So this is something that you ought to commit to memory so you can do this, is what does the P stand for? How do you use it? Okay? Negative log of X or H or whatever. All right, we're good on that? Okay. All right, so let's talk about drinking water. Shift gears here. Of course, we will use chemistry in the drinking water, but today we're going to go over some of the fundamentals. What motivates us to treat the water? Kind of what are some of the standard approaches? What are the baselines for our regulations? I think we'll have enough time to also get into sedimentation. So how can we use gravity, basically, the cheapest thing, physical process available to start our water treatment process? Because ultimately we want to treat water well, but we want to do it as cheap as we can to provide cheap, close to free, clean water, right? That's would be a great thing to do. So, fundamental motivations. Well, it turns out that one of the most important and common reasons to treat water is simply that we have to avoid drinking dirty water, right? Obvious. We don't want to get sick. And it turns out that one of the main pathways to disease is what's called the fecal-oral route of transmission. So, sounds kind of gross. It is kind of gross, but we can imagine if we want to be drinking some water, but upstream we have some sort of waste entering the stream, right? So we have a toilet, flushes the toilet, and now we have a source of fecal contamination in our water? Well, it turns out this is kind of wastewater treatment in some sense. The waste has to go somewhere. So where does it go? Well, if we discharge it on the street, well, it's going to find the lowest areas, just like when it floods, right? It's going to find the closest river, stream, down gradient of that spot. And so fecal matter is going to enter the rivers and streams. And even if we didn't do that, well, there are also animals out there, and you can enjoy my stick figure, whatever it is. Some mammal, probably. Warm-blooded animals tend to have similar pathogens because it's similar gut environment. And so we need barriers, right? And so my point with the silly drawing is that we put a barrier here, right? We make a barrier and we say we're going to have some drinking water treatment. Of course, it depends on what kind of source we're taking from. Maybe we don't need much of a barrier, just kind of a protective layer, but we need to make sure that we have a barrier. Let's say if we take groundwater, which is the case for Baton Rouge, the groundwater we are tapping into is very far removed from any sources of fecal contamination, at least modern ones. And bacteria, while they can live a long time, if you don't have a source providing them, there doesn't tend to be very many pathogenic bacteria hundreds of feet deep into the soil, groundwater, all that. So if there's no sources recharging it rapidly, then by the time water makes it down there, the natural filtration and the natural competition from other bacteria, a natural decay of the bacteria that might harm us, it ends up being a pretty safe supply under most circumstances. However, if we are in New Orleans, well, the groundwater is too salty, so we would have to use the river water. So we definitely need strong protection, strong barrier there. Now the other barrier would be here, and this would be our wastewater treatment. So we will often have, we elect to have both, and that's a good thing because now it's a bit safer to have contact recreation with our water bodies. And it's a bit safer to use our water bodies as drinking water sources just in case our treatment was not sufficient. We could imagine a scenario where a drinking water source became extraordinarily contaminated and our typical treatment is not sufficient. So we want to avoid that. It's good to have both barriers, even if there's still animals about and all that. Okay, so that's kind of the fundamental first motivation for drinking water treatment. This is a lot of what public health is about. If you were to look into epidemiology, for example, the origins of it, which I think we'll talk about maybe today or maybe when we get to disinfection in particular, really has to do with how do we know why people are getting sick, what's causing it, and in many diseases that are pretty much no longer existent in modern day, were fecal-oral route of transmission. Poliovirus, for example, is a fecal-oral virus. And there are sources, I think rodents, the only polio remaining in the world, primarily the source is rodents. And so when you have good barriers for both of these, it's almost non-existent, right? It's just we simply don't have exposure to it anymore. Typhoid is another example. Cholera, lots of diseases you've probably heard of that were rampant and really destructive many years ago are almost non-existent now. Okay, so I mentioned it kind of depends on where we're getting our water. We could consider getting rainwater. We could consider getting ocean water and desalinating. If we have glacier water, that's pretty clean because that came from rainwater basically and precipitation and probably excluded a lot of the stuff as it precipitated there. Surface waters, groundwaters, rivers, lakes, swamps. You can imagine all sorts of places you could get your water, right? And then the treatment that is required is going to be largely dependent on where you're getting that water. Now, for the sake of the class, we're probably primarily going to focus on situations where we would get our water from the surface water. That'll give us just the most generic drinking water train process train, whereas Baton Rouge, for example, we just need less processes because we're taking the good quality groundwater, and we don't really need to filter it so much to remove particles. That's already naturally accomplished. So we're going to go through as if we're taking river water so that we can kind of see the full picture. We're not going to dive too much into desalination. We can talk about that a bit. Most of desalination comes down to energy. It's simply going to cost energy to force water away from salt, or force salt away from water. And that is osmotic pressure. And no matter what we do, whether it's evaporation, if it's reverse osmosis, the membranes, it's going to cost energy. And so the good news is, kind of on a global scale, if you ever hear somebody fear-mongering about running out of water, that's kind of baloney, first of all, because the water cycle does recirculate quite nicely. There might be water shortages that are important, but as long as we have energy, then we have access to clean water. Energy and some infrastructure. The simplest would be to boil water, right? To drive that evaporation. That's more expensive, less efficient than if we had something like reverse osmosis. But running out of water is not a thing. There's so much water on the earth. It's a matter of cost, and it's a matter of managing the costs, managing the price you're going to pay. If you're discharging a whole bunch of salty water, you probably better pipe it out further into the ocean so you're not going to kill a estuary system with super, super salty water. There are costs involved, but costs that can be managed. So energy is really critical, and some infrastructure in place. And the same principle applies to basically any type of treatment, right? We could take the space station, for example. Where do they get their water? Whatever they brought with them. That means what happens to their wastewater? They need to use every drop of that. And they have to treat it accordingly in order to be able to reuse that. So they have enough sophisticated infrastructure to do so and to have a closed loop of their water cycle there. Otherwise, we're going to be shipping tons and tons of water up there, and that's going to be an enormous cost. Okay. Now, to put this into a bit of context, looking at kind of an engineered sort of a situation, this is an image from our book. We can consider if we have a wastewater treatment plant, we might be getting water from a stream, maybe a lake, reservoir, or a well. Whatever the case, we're going to design that drinking water treatment plant and then distribute. And oftentimes we consider the distribution itself as also kind of part of the water treatment system, because we need to protect the water from any infiltration of water coming from the ground. And in this case, if we're 4 feet under the ground, or maybe a couple yards or whatever, that's not very protective in terms of there's very likely contamination, like pathogenic contamination in the surface groundwater. Animals, sewer lines, all sorts of stuff, right? So when we operate our distribution systems, we always treat them as if this is part of the treatment process so that we know we're managing how much residual disinfectant is there. We're making sure that if there's a pipe break, that we have to account for that pressure drop because we might have let bad stuff in. And we always operate on positive pressure because if we have a leak, we want it going outwards instead of inwards. Okay, so then it goes to homes, maybe industries. Sometimes maybe they have to treat it more. Maybe they get their own water supply. Whatever the case, they'll produce wastewater, and later on in the course, we'll talk about the wastewater treatment, and then, of course, back to a river where maybe we will have downstream another drinking water treatment plant, right? If you think of the Mississippi, there's certainly many wastewater sources entering it, and eventually people downstream are going to use it, right? So that's simply always going to be the case. Some natural processes help mitigate that, but we also have our barriers here. Okay, I already talked a fair bit about this. If we take a look at when typhoid fever, like in history, when it was a problem and when it was no longer so much of a problem, This is a graph of the number of deaths per population, per 100,000 population per year. And in 1900, there was 25 or so deaths for every 100,000 people dying of typhoid fever. Chlorination, the first time we started applying chlorination was right around 1910, and it began dropping right alongside that. Of course, chlorination wasn't everywhere and probably wasn't done quite right everywhere that it was applied. And of course, we probably didn't have great barriers for the wastewater side at that point yet either. But this is a pretty good show of kind of the impact of breaking that fecal oral route of transmission. Okay, so obviously we don't want to get sick, but what else do we care about? Basically other ways we might get sick, right? Anything that could cause a toxic or a pathogenic response. So the Safe Drinking Water Act of 1974 really puts into place the regulations that we are required to meet if we're doing a public water utility to protect health. So protection of human health is the primary goal for these standards, and we actually treat our drinking water standards in two categories. One's primary and one's secondary. The primary, these are enforceable by law. If they're not met, it's a big problem, and legal action ensues. These all pertain to health effects. These, in terms of the toxins, there's often what we would call maximum contaminant levels identified So for example, maybe it's safe enough to have 1 part per billion of hydrogen sulfide. It's not at all toxic at that level. It's no problem. Nobody really cares if it's in your drinking water. But at some threshold, it's a potential health risk, and we're concerned about it. So we might set a maximum contaminant level that is safely under that problematic threshold and say, okay, as long as we never go above this, we're not really risking anything. So that's just one of several ways of regulating. Sometimes there's more of a technological requirement to say, you must use a technology that disinfects X number of pathogens, and if you do so, we then assume it's safe, and we're going to monitor for pathogens in this manner, but we're not checking every second, every ounce of water, right? So sometimes it's a little more technological and monitoring, and sometimes it's something you can monitor more closely. Okay, so the primary standards include chemical, radionuclides, and microbial contaminants. Pretty obvious, all those things that could cause you health problems. Secondary standards, and I think I might have mentioned this on our first day of class, these are aesthetic. So I think with you, I asked how many of you like to drink brown water. I say that? Yeah, and I see at least a couple of you with soda and stuff, right? It's often we want water to be nice and clear coming out of our tap, but sometimes we make it brown because there's flavors that we're adding with the coffee or the tea or whatever. And it's aesthetic. It's fine if the water is now colored and safe to drink, safe enough. So technically, it could come out of our tap and be aesthetically displeasing, but legally fine as long as it's meeting all the health issues. Of course, we are, just our intuition says that looks bad and maybe we shouldn't drink that. And sometimes that's very important. But nonetheless, that doesn't technically mean anything legally, so long as there's no actual problem there. So it could be taste, odor, temperature. Temperature actually affects how much oxygen is dissolved, and turns out that dissolved oxygen tastes better than lacking oxygen. So it's something we can actually taste. Color and then hardness, I think I mentioned probably as well. It's how much mineral content is in there. Might change the flavor a little bit, might cause scaling like around your sinks or something as water evaporates in spots, leaving behind some mineral residue. Tends to be just unpleasant, and it also changes the way soap works with your skin. We'll talk a little bit about that with coagulation. And it's just, yeah, it's an aesthetic concern. Some industries, hardness becomes much more than aesthetic. They have to remove hardness so that they're not clogging up their machinery with minerals. So sometimes it's a really big concern, but for general use, no big deal. This does not apply to private wells. So private water systems are not regulated because they're private. So there are certainly recommendations and standard practices and everything, but this is all for public water systems. Okay. All right, here's a graph of hardness in the US. Just as a quick little note, I grew up a little outside of Atlanta, somewhere around here. Pretty soft water if we look at the scale. The purple is the softest type of water. Blue is a kind of medium softness. White is kind of hard water, and then red is very hard. Then I lived for 2 years right up around here, so much harder water. And then, of course, now we're down here in Louisiana, and you see, might be a little hard to see where the borders are, but we have some hard water and some areas of soft water. So Baton Rouge proper, it's mostly pretty soft water from the aquifer we're getting from. So you might experience, if you're from somewhere else or if you visit somewhere else, you might suddenly think to yourself, wow, I'm trying to wash my hands with soap and it's just, there's no bubbles. I just need tons and tons of soap. Or if you were used to somewhere that's a little harder and then suddenly you go somewhere with really soft water, you might think to yourself, I just can't get the soap off me. It just feels like it's never leaving. What's up with this? That's actually the dynamic and one of the more tangible ways you can see that. Okay. So where do we start with the treatment? Well, this is the typical surface water treatment plant that I was mentioning. This would be a typical process if we were treating from a river or a lake, something like that. And we're going to start with sedimentation, but real quick, the overall picture, and we'll revisit this a few times. We'll do the same for wastewater when we get there. We're going to have an intake, and we need to block out any fish that might be trying to get in, any basketballs that might be floating down the river, or whatever. You know, probably we're not at the surface, but whatever happens to be there, we're going to have an intake structure that prevents stuff from coming in as best as we can. Inevitably, there's going to be some sand, some grit, some small particles that were washed in, whatever the case. And then, so that'll be the first step once it reaches the plant, is to have a finer screen and grit chamber to really stop anything that could mess up our plumbing, for example. It would sediment out in seconds. It's like really quick to remove it. Just go ahead and get rid of all that kind of stuff. Anything that might be that you could do with a very simple screen. And so we'll have some automated system more than likely to get rid of that. That's going to be a process that we see in wastewater as well. But there it's even more so, lots more junk collecting. Then we're going to send it to sedimentation. And we'll say primary sedimentation because we're very likely going to use it twice. So we'll have sedimentation, any of the very fine sand or some of the soil particles or something that can settle out of water if we get it some slow quiescent flow for a little bit, kind of the opposite of turbulent. Just let stuff settle. Use gravity. The water's just, the expense will be having enough area to let water slowly flow through it at the demand we need. Nice and cheap otherwise, and it's just good to use gravity. After that, we typically are going to do a little bit of a chemical process to improve our ability to sediment the rest of the stuff, the rest of the particles that can be removed. So the first steps are really all about the physically removable things. When we get down to trying to kill viruses and stuff, technically we could filter them out, but usually chlorine is a lot cheaper and does just fine at killing viruses, for example. So we're going to use sedimentation, then we're going to do something called coagulation, and then give it some time for flocculation. Olivia mentioned these actually in her presentation just a little bit ago. Oftentimes this will be a coagulation dosing chamber and then a flocculation chamber. If you have a smaller scale system, maybe you can do it at the same time. And then also you could potentially even just do it all in one bottle and then let it sit there and let things settle. So it's technically possible to do all this in one reactor, but it's going to be in batch mode because you have to add the coagulant, mix it kind of slower. As we'll talk about, we need to let the particles meet each other and then stick together and grow larger and larger. And then we have to stop moving them at all and let them sediment. So the whole point of all this is that we can use a bit of chemistry to improve gravity's action. Okay, so we've got gravity here, and then we're going to give it a boost. We're going to make larger particles with some chemistry. We're then going to make use of gravity again. Occasionally we'll have a system where maybe we'll skip that and go straight to a filtration step. But we'll talk about both. We'll gather that sludge and then send that to some wastewater type processing because that'll just be junky, grungy, gross stuff. And then once we have most of the solid and particulate matter stuff taken care of, we expect there's probably still some bacteria that are just too small to sediment and not stuck to any particles that we did sediment. And viruses, the sedimentation is not really going to do anything for those. We'll see the particle size makes a big difference, and those are just too small. So we need to get rid of those. And unless we're doing a fancy filtration for that, typically we'll do like a non-fancy sand filtration. Just helps grab more particles. So at that point, we need to disinfect. And so by then, our water's pretty good. We'll disinfect. Maybe we'll add some fluoride. Sometimes we use that as a tracer. Has potential benefits for dental health. Sometimes we'll adjust hardness if we need to. We'd probably do hardness adjustment here if we're going to. And in general, we just polish the water up and send it out. And then the distribution system, like I mentioned, we are typically making sure we have the appropriate residual chlorine concentration there. Okay, so we're going to start with sedimentation, and that's my next set of slides. Okay, so we talked about this and this. All right, so the point of sedimentation, like I mentioned, is to simply use gravity, right? Now, we can make a few assumptions about the particles that will simplify all of the math and make it so that we can derive exactly the equations that we need together today, and then you'll also have that equation on your exam, okay? You'll have the equation for how fast these particles will settle. I'm going to give that to you. The point of deriving it with you right now is a couple reasons. One, so you kind of have a good understanding of what's going on here. It's physics you've learned before. And two, you know what the terms are that's going into that equation, right? So this hopefully will familiarize you with what's going on. So first of all, we have some particle. On the left here, that's maybe what a typical particle might look like. Kind of weird looking, different shapes. Nothing too regular or easy to model mathematically, so we'll just assume they're perfect spheres because that's easy. And it turns out it actually works pretty well for the type of calculations we need to do. A lot of sedimentation, if you really get down to it, it ends up more complicated than this stuff that we're going to talk about, although we can use this as a big picture scale of what's going to happen. If we really get down to it, we can't calculate exactly enough, and then we do certain experiments to just simply see how much coagulant do we need to dose with, or what are the conditions. When particles get so thick, they start making a blanket, the sedimentation dynamics change. So we're just going to make some assumptions that that stuff's not happening, which is true for most of the sedimentation process. And we're going to go with a sphere so we can calculate with some physics. And we won't really dive into the more complicated, more empirical side of stuff. So what are the forces acting on a particle? If you stop and think about it, particle floating in water, what's acting on it? Well, it's all written here already. So we have the force of gravity. So we can say F of G. That's going to be opposed by a buoyant force. So F of B. If you take a beach ball in a swimming pool, well, try to put it underwater, it's going to float. We're displacing a lot of water for a tiny, tiny bit of mass in that air. So if we have something more dense, put a bowling ball in the swimming pool and it's going to sink. As it sinks, there's going to be another force acting against it, which would be a force of drag. So assuming that our direction of travel is downward, then the drag force will be upwards. Now, technically, there are systems that reverse this, and they do something called dissolved air flotation. They bubble up a lot of small air bubbles. They attach to the particles, and then the particles are moving upwards with a buoyant force, and you have a drag force going downwards. Don't worry too much about that. It's just another thing we can do. It's going to be approximately the same math. So the principle here is we can use a force balance to find our velocity, right? So a lot like skydiving. At what velocity do you reach equilibrium, a steady state, or a terminal velocity, and you are then just falling at that speed, right? What we're after is to find here a terminal velocity for a given particle, and to understand what that depends on, right? So a force of gravity we can describe as the mass of some particle or some object times the acceleration due to gravity, right? That's right here. So if we describe the force as m times g, that makes sense. We've seen that before. The buoyant force is going to be the mass of the water displaced times the acceleration due to gravity, because it's the mass that's displaced that would rather be sinking, that mass of water times the gravity, that's going to cause the buoyant force pushing upwards, opposing whatever's displacing that much water. You can think about it like if you drop that bowling ball in the water, it's pushing that much water away, which is now in some sense above it and would like to come back down, caused by gravity pulling it, the water downwards, right? So it's a boat floats because there's enough water being displaced that it's pushing back up in that sense. Okay, the force of drag is going to depend on the dimensions of our system and the viscosity and stuff like that. So we can say that I have all of this labeled out and all the terms there on the next slide. So I'll explain each term in a moment, but we have one term for gravity, that's mass times gravity, buoyant force, mass of water displaced times gravity, and then the force of drag, this is going to be 3 times the dynamic viscosity times pi, that's coming from the sphere, times the velocity times the diameter of the particle. So the 3 pi and diameter, that all relates to the surface area, the amount of water that's it's going through some area. And what I want to highlight is the Vs, the settling velocity. That's what we're after. So we're going to solve a force balance with these 3 forces to find this Vs. That's kind of the point. Okay, one more comment here. Well, first of all, we can say the force of gravity, once we find the terminal velocity, will be equal to the sum of the buoyant force and the drag force. That'll give us a force balance, right? So once we reach our terminal velocity, those are all the same, and the net acceleration is 0 because the net force is 0, right? That's kind of the assumption. Now, coming to the force of gravity and the buoyant force, we see here we have another way of writing it. Instead of mass, we can say the volume times density. So volume times mass per volume, which is density, clearly is mass, right? I'll just write this as density. So the reason we might want to do this is because it's actually pretty hard to weigh one little tiny particle. If you've ever used a little mass balance scale in a chemistry lab or something, or even just one at home to weigh something, you recognize you're going to have trouble weighing something too small. If you tried to weigh my water bottle on your scale at home, you might think to yourself, that's probably not going to work very well. Like maybe if I stand on it and pick it up, I might notice that 1 pound difference if it's full water bottle or whatever. Or if you're in a chemistry lab and you say, okay, I could weigh 1 gram of this and probably like a couple, maybe 5-10 milligrams, not too much trouble. But if I try to go much lower than a milligram, A, I need a very fancy one, and B, I can't go much further than that. Really, if you get up to like tens of micrograms, you're in good. You're doing great. Like that's incredibly fancy mass balance. If you think of the weight of one of these particles, you're probably well beyond that, like well below that. So we're not going to pick one of these out and weigh it, but we need to know the mass. So what we can do is collect a bunch of them, measure their average size. That's actually fairly easy with some light scattering techniques, amongst other things. Could just even do filtration. And we can also find their density without too much trouble once we have a bunch of them, because that's the amount of, we can measure the displacement and stuff like that. So we can get measurements or estimates for density and volume a lot easier than we can picking out one particle and seeing the weight. So that's what we're going to do, is we're going to use particle density and the size of particles. Here we're saying volume. A lot of times we'll use diameter of the particle, which we also see here in the drag equation. But we can get a volume from a diameter of a sphere, and we'll just do that math and it's no problem. So all that to say, we're going to use the size of the particle and some knowledge about its density to get that. Now, in the case of the buoyant force, we have density here of water instead of the particle. We know the density of water. We've got the lookup tables for that. Depends a little bit on temperature, but it doesn't change a lot. So with all of that, if we know something about the size of the particle and an estimate of its density, we're pretty much good. And we can do these calculations. Okay, so all of that is written out well for you here, so we can understand which piece goes where. So mu here is the dynamic viscosity of water. Our units will be kilograms per meter per second. That's this guy. So that's kind of telling us how viscous the water is. This is temperature dependent. So when we have a lookup table for the density, we also look up the viscosity of water. And you might recognize this if you've worked with some other liquids. You probably didn't necessarily notice that viscosity of water changes, but let's say honey. If you have a bottle of honey and you try to pour it on something, you know that that's pretty viscous. It's hard to flow. If you were ever to heat it up and put it on something, it gets a lot more slick and a lot more likely to make a mess, and you accidentally get it everywhere. You've probably recognized that if you've ever done something with heating honey, like a peanut butter honey toast sandwich thing or whatever. Okay, so that's dynamic viscosity. The Vs is the settling velocity. This is our target that we want to find an equation for that with this force balance. dP is our diameter of the particle, and we're going to leave that in meters because all the other units we're using meters. The diameter of one tiny little particle in meters is a very small number, right? So just keep in mind, we're going to be dealing with like micrometer level stuff-ish, maybe 10 micrometers. So that's going to be like 1 times 10 to the minus 5 to 6 range in meters. G is the acceleration due to gravity, again meters, and again seconds. right? So it's 9.81 meters per second squared. M is going to be the mass, either the particle or the water. Have a little subscript there. V, the uppercase V, P is the volume of the particle. This rho, that's density. So rho P is the density of the particle in kilograms per cubic meter, and rho with no subscript would be the density of water, kilograms per cubic meter. And remember, that's temperature dependent. So we'll have a lookup table for this and the viscosity. So this is also temp dependent. So if you're not given this, you'll have the table and you'll look it up from the table. Okay? All right. So with that, hopefully we can set up the force balance using these equations and solve for Vs. Okay, so that's next step. So how to find that terminal velocity? As if the particles are little skydivers. So let's set it up. Fg is the volume of the particle times the rho of the particle times acceleration due to gravity. Force, buoyant force is very similar. Volume of the particle times the rho of the water times acceleration due to gravity. Force of drag is the different one, and here we have 3 mu pi times our Vs that we're going to solve for times dp. Okay, so what I'll do is just get the Vs term by itself and say Vs times 3 mu Vs, just move that, 3 mu pi dp is equal to volume of the particle times rho of the particle times acceleration due to gravity minus a lot of the same terms over here, Vp, rho, water times gravity. And we can divide everything by the 3 mu pi dp. So we'll get Vs equals, and I'm going to go ahead and factor out everything that I can on the top here. So I'm going to say Vs, Vp, volume of the particle, that should be uppercase V. Vp times G, factor those out, we'll be left with the rho of the particle minus the rho of the water. All that divided by this 3 mu times pi, diameter of the particle. Now, we could maybe leave it there, but it's going to be much more convenient if we go ahead and take the effort to convert from volume to diameter and simplify a little further. Because right now we have this in terms of diameter and volume, but really, if we're assuming a perfect sphere, we have an equation for that, right? Anybody happen to remember the equation for the volume of a sphere? I think that's correct. 4 over 3 times pi r cubed. Now, if we change that to diameter, that's going to change it up a little bit. That makes sense? Everybody agree with that? That should be it, right? I always kind of have to double check myself too. So if we want to convert this to diameter, we're going to take 4 over 3 times pi, and then instead of r, we can put diameter divided by 2 and cube that whole thing. So that becomes 4 pi divided by 3 times 2 cubed is 8. So 4 divided by 24 times diameter. So that's going to be pi times diameter over 6. And we can put the p to indicate that that's the diameter of the particle. Okay, does that make sense? Good on that? So we just converted the volume equation to diameter, Oh, excuse me, there should be definitely a cube there. I saw at least one face that was like, what's going on? And hopefully that's it. What is this craziness? Okay, so yes, volume is in 3 dimensions, so it makes sense that our distance should be in 3 dimensions. Okay, given that, we can substitute here and say this should be, I'll go ahead and put pi dp cubed times g times rho minus rho p minus rho water, divided by 6 times 3 times mu times pi times dp. So we'll see this should simplify pretty nicely, and we'll be left with a final equation that says, well, the pi's cancel, and 2 of the dp's cancel. So I'm going to write this exactly how our book has it. It'll be the acceleration due to gravity times the rho p minus rho times dp squared, all divided by 18 times mu. And I'll highlight this. So this is the equation then you'll have on the exams. And now hopefully you understand where it comes from, right? And so then you have an appreciation for the 2 densities there. You have an appreciation for these units. We have to have kilograms, meters, and seconds. So if you're given a problem and you're given diameter in micrometers or millimeters, you recognize you're going to have to convert that. And you have to remember, what is a micrometer? It's 10 to the minus 6. Millimeters, 10 to the minus 3. So if I give you 0.01 millimeters, that's the same thing as saying 10 micrometers, which is the same thing as saying 10 to the minus 5th meters, or 1 times 10 to the minus 6. Excuse me, 10 times 10 to the minus 6 meters. So you can do all that, you know all that. Remember also that when you do the lookup table for mu, the table that we have has a times 10 to the minus 3 for dynamic viscosity. So make sure you fully get the units, including that, into these when you solve the problems. The other thing you'll have to do is convert. Pretty often you'll get a density value. The lookup table gives us water in kilograms per cubic meters. So for density, it's very often kilograms per cubic meter, especially for water. But rho of P could be in something like grams per milliliter. That's a density term. And you're going to have to convert that into kilograms per cubic meter. So just warning you, there will often be some units you have to deal with given some problem. Given just the way that the density of particles is typically measured and reported, then you have to do the conversions. Again, you can do that. It's just a matter of doing it. One thing I'll say is you can kind of use a cheat code a little bit if you recognize the density of water is almost always near 1,000 kilograms per cubic meter. Also, like saying near 1 kilogram per liter, right? So given that you know that, and it's even in your lookup table, it's approximately 1,000 kilograms per cubic meter. And if your particle is going to sink, it should be at least 1,000 kilograms per cubic meter in density. So when you do your conversion, you can double check that if you're getting a 0.00 number, you're way off. If you get a density value of 5 kilograms per cubic meter, that's going to float real fast, so you're probably still way off. If you get something that's like, 1,500, okay, that should sink, and you're probably in the right range. If you get 10 million, that's going to sink very fast, and you're probably in the wrong range. You probably did something wrong. So double check yourself, check the units. Sometimes you'll have something like 1.5 grams per milliliter, and if that's, I'll just tell you, if that's a problem I've given before, then I've done the conversion before, and then I can even just assume that's going to be 1,500 kilograms per cubic meter. Now, I'm not going to keep that here because I'm not double checking myself on this right now, but if I give you some conversion, there's a good chance it's approximately that on the scale of 1,000 something, or maybe 2,000 something. Just double check yourself there. Otherwise, this is all quite straightforward, and we can plug it into typical physics. And I think we'll start there next time, whether that's Thursday or a week from today. Last thing I'm going to say is just that it'll be physics of watching the velocity, how fast is it traveling, all that. So be safe, stay dry, or try, and have